We have a number of samples here submitted to the laboratory from the crime scene examination. We have some suspected hair fibres. We have some suspected hairs and some textile fibres that have been recovered from the crime scene. Here we have the Foster and Freeman Ffta, the Trace Evidence Analysis System, and we're going to be using the UV-Vis NIR microspectrometer module to examine the textile fibres, and we're going to use the VSC style imaging suite to examine the suspected hairs, where we can do some annotated measurements and overlays to help us with our comparison. Here we're going to take a look at the UV-Vis NIR microspectrometer. It records absorption and transmission spectra in the range of 240 nanometers to 1,000 nanometers. We have a fibre here mounted on a quartz slide in glycerin, and we're going to use this system to take some absorption measurements of these fibres that are recovered from the crime scene. Okay, so the first step, here we can see we've got the fibre in focus. We need to record our white reference or our transmission reference. So we'll click that, and then the system will automatically determine the scan time based on the amount of light that is transmitting through the system. And it will record that 10 times, which I've set here as the number of repeat measurements it will take in order to create a spectral average. Okay, this just improves our signal to noise. Okay, once it's done, we click OK. And now we need to record a dark reference. Okay, so once the white reference and dark reference has completed, we just now need to position our fibre under the crosshairs, as indicated on the live video feed. Make sure that the fibre is in focus, and we can record our spectrum. Okay, it will use the same parameters that it took from the white reference to then record the absorption spectra of our red fibre. The measuring aperture, depending on the objective that's used, for the UV system we use a 40 times reflective objective, and our sampling aperture is approximately 1.25 microns. So because of that, we're going to have to take a few repeat measurements of the sample just to sort of build up an idea of the range of variation that we're seeing across the group of fibres. Typical number of measurements for man-made fibres would be around 5 or 6, and because natural fibres tend to exhibit more variation, typically you would take somewhere between sort of 10 and 12 measurements. So we'll take 5 measurements for this particular fibre here that I can see as a man-made fibre, and then we'll repeat the process for our questioned fibres. Okay, so once we've recorded our repeat measurements for the control fibre, we're now going to place in our sample already prepared for the question fibres. So we just need to swap the samples over, and then we need to find those on the slide. There we go. Get that in focus. Because we've now swapped the sample over, we would now need to record the white and dark reference measurements again before we start taking our spectral measurements of this fibre. So now we're going to take a look at the Ffta imaging suite. This is, again, custom software, actually originally designed for our video spectral comparator systems and adapted for our Ffta microscope system. The imaging suite allows us to take advantage of the 5 megapixel Gigi camera to allow us to take high resolution images, and also calibrated measurements of our trace evidence. So place the sample in, and then we're going to just find our evidence of interest, and here we have our red fibres that we were looking at earlier on the UV vis microspec. Okay, so get the fibre in the appropriate position and get it in focus. So here we can use the software to take high quality images of our fibre. We can use the Annotations and Measurements function to either annotate the image with some information, so we can put a text box on, annotate it with the details that we require. We could use it to point out features on the fibre, so here we can see the particles of delustrant, and we can use the software to point out features of interest. If we check the objective that we're using, here we're using a 40 times objective, we can set that function in the software, and we can also now use that to take accurate calibrated measurements, in this case the diameter of the fibre here coming in at 20 microns. Once we're finished with that, we can make those annotations permanent, and we can send those to our recent images gallery or save the images as we wish. Okay, once we've finished with that one, we can now take some images of our other sample. Okay, so here's our red fibre. And again, we can see that this time there's no delustrant particles. We can take our measurements again, take our accurate measurement. If you want to take a few across the width of the fibre, if there's a bit of variation, you can take as many as you need. And then we can make that annotation permanent and send that down to the recent images gallery. Let's take another one without the annotations. And using the software, we can now do a side-by-side comparison as well of these two fibres. So we can switch to side-by-side. We can keep this one as our live measurement if we want, and then we just need to drag and drop our sample from the first examination over into our second window here. Because we've got it live, we can reposition our sample to be in a similar orientation to the one that we took before. We can see that side by side they are in fact very different physically. We can use the imaging modes to perform an overlay as well, so we can mix the two images together. We can use the software to superimpose the two images over the top of one another, like so. And then we can use various imaging features like a horizontal split, where we can look at the two with a horizontal split or a vertical split. So here we can really point out the differences between the fibres. We could put on a strobe effect, so we can strobe between image 1 and image 2. And with a split image, we can of course capture that in here. We could then just go back to the single image, and again we can then drag and drop back into here as our sort of stored image, and again we can sort of go back to the annotations and measurements if we need to. So here we can sort of point out various functions, features, like so. If I go back to the side by side, again I can very quickly drag and drop the images that I recorded earlier, and here we can also see that the size of the fibres are quite different. The fibre here on the left-hand side is about 15 microns. And then the other fibre over here we're comparing it to is about 20 microns. So quite easily we can generate high quality, high resolution images and use the calibrated measurements function to take accurate measurements of our samples.